We use vectors a lot in math and science, and you have done vectors in physics, so hopefully it's not that big of a deal. But consider that here we have A, and we have a vector that goes to B. So a vector is a directed line segment. So let's define a vector as a line segment with magnitude and direction. So what that means is it has both a link and a direction. Now notice that this vector has what we call an initial point and a terminal point. So we have a starting place and an ending place, and they're called the initial point and the terminal point. And it's important that you talk about them correctly. And the notation here is this is called vector AB. So it's written with an arrow over it or a half arrow over it. So it's a vector AB. If we put a letter on it like V, we could call it vector V. Textbooks use bold notation to indicate a vector when it's a single letter, but we don't have that. So we could say that vector V is equal to vector AB. And I tend to use that for vector notation. It was very common. So that's what I've always used. If you have two vectors that are exactly the same in length and direction, well, that's not quite the same, but we'll pretend for a moment. So if you have two vectors that are the same, then we could say that vector CD is equal to vector AB. And that's common notation. They're equivalent or they're equal. There is such a thing called the zero vector, and it has the length of 0. It's the only vector with no direction, so that's important to catch. Let's say we have two vectors. Let's say we have vector A and vector B. So if we want to add vector A plus B, remember the head to tail rule? So you're going to pick a vector to start with. I'm going to pick vector A, and we're going to pick vector A to be here. And then vector B, you put the head of B to the tail of A and add them that way. And then your answer is the resulting vector. So this is vector A plus B, and it's called the resultant, and you can see that that's happening there. There's also the triangle law, and the triangle law says that if you take A, I think it's about like that, and B, and you put them tail to tail, then you could draw a parallelogram from there, and from this side you could put A, and from this side you could put B, and it forms a parallelogram. And the answer from your original point to the second intersection is your resultant, which is your answer. I think it's a whole lot more work to end up with the same thing. So keep that in mind. It's pretty good. So a vector has both length and direction. So let's say we have a scalar, and let's talk about what a scalar is. A scalar is a constant, and it's often used to be the letter C because it is a constant. And so we have C times vector V. So what it is it's kind of a multiplier. If you multiply it by a positive number, it increases it. If you multiply it by a negative number, it reflects and it increases. So let's let this be vector V, and let C be 2. Then what that means is we're going to take vector V twice. We're not going to actually put the arrow in the middle. I just did that because I'm eyeballing it, and it's not always a good plan. So let's erase that little symbol right there. So this would be 2 times V right here. So it's the same as CV. Let's say that C equals -3. So CV would be, that means my V goes in the opposite direction. There's 1, there's 2, there's 3. So this is -3 times vector V. So if you keep the fact of the negative in mind, then let's talk about if you are given, let's say you're given vector A, and let's go back to the vector B that we are given. Then if we wanted to do A minus B, we would start with A here. Oh, that's a little longer than our given A. Let me try again. It's about that long. So here's vector A. And then negative B means instead of going this way for B, we're going to go the opposite direction for B. So the resultant is the tail of the first to the head of the first to the tail of the second. So we have A minus B, and that's our resultant there. It can also be done using the parallelogram law, but I think it makes it harder. So just run with it that way, okay? For a lot of what we do with vectors, it's easier to think about them algebraically. So we're going to say we're going to let letter A be A1, comma A2. This is these brackety, instead of parentheses, these pointy parentheses, we call them vector notation, are the notation for vectors. And then in three space, we'd say A1, A2, A3. That's our common notation. So this is in two space and this is in three space. And they're the components of vector A. So if you think about vector A in two space, it would be a vector here, A1, A2. Now, this is the vector A1, A2. It ends it ends at A1, A2, and this one begins at 0, 0. So you can see how it forms a vector in that aspect. And then in three space, you would have the same concept. So we have A1, A2, A3. I'm going to use a different color. So right here, we have a vector. This is A equals A1, A2, A3. So we tend to do it either graphically or algebraically, but not both. Sometimes we'll do both to help us see it, but it's not as big of a deal. If you look at these vectors, the original vector, let's say the original vector is this one right here, that goes to point P32. So that's 0.32. So each of these vectors is the same length. Notice that it has a length here and a direction. So each of them, we could kind of think of it as a slope of 2/3 because you can kind of see it goes up 2 and over 3. That's not how we generally talk about it, but it's going to help us to compare these. So all of these vectors have exactly the same magnitude and direction. So this is vector P. It's just moved all the way around. The one from the origin to point P, this main one right here, is called the position vector because it's actually the one that starts at the origin to the length of P, so it's easy to find the length. And when you think in terms of Calc 2 and all the thing in calculus and all the things you've learned, that like in polar coordinates and stuff, this is the x-axis is your pole and this is your main angle. So it kind of helps you figure out that that's your position vector. The same thing is true in three space, but I'm not going to try to draw it for you. But in a three space, if you have the position vector of OP, it goes from the origin, which is the vector 0, which the component point is 0, 0, 0. So in three space, your 0 vector is written like this, and it means that you have the point 0, you have the vector 0, 0, 0, which doesn't go anywhere, has no length. So the the vector OP in three space starts at the origin and goes to some point A1, A2, A3, like we talked about. So the next part, okay, so given points A, which is x1, y1, z1, and B, which is x2, y2, z2, then we can define vector A to be the point AB. That means it starts at A and goes to B, um, x2, it ends at B, so it's x2 minus x1, y2 minus y1, and z2 minus z1. So it tells us the components of the vector. An example of this, that's actually like something in a box. It's kind of a big thing to know. It's intuitive, so it's not something you really need to memorize. So example, consider that A is the point 2, negative 3, 4, and B is the point negative 2, 1, 1. Then we can talk about vector AB. That means it starts at A and ends at B. And that would be negative 2 minus 2, which is negative 4. 1 minus negative 3 makes it positive 4, and 1 minus 4 is negative 3. So vector AB would be that vector. And vector BA means we start at B and go the other way. So it's 2 plus 2, which is 4. 2 minus negative 2 makes plus 2, which is 4. Negative 3 minus 1 is negative 4, and 4 minus 1 is positive 3. Now notice they're negative versions. One of them is a negative of the other, and it's because the direction goes the opposite way. So that's a really cool thing to think about and work with and play with. Next, we are going to talk about the magnitude or the length of the vector. So if you have a vector A in 2 space, it's A1, A2. And the length of A is notated this way. This is your length of A. And the length of A is equal to the square root of A1 squared plus A2 squared. So think about the fact that you have a vector in 2 space. So this is A1, A2 is our point. So our vector is A1, A2. Then the distance between the two, we could say that the distance equal to the square root of x1, which is A1, minus x2 squared, plus A2 minus 0 squared. So the distance of, or the length of that is A1 squared plus A2 squared. Kind of makes sense, doesn't it? Now, here's what's really cool. If we put it into 3 space, we're going to let A equal A1, A2, A3, and R3, which is our 3 space. So that means that the length of A equals the square root of A1 squared plus A2 squared plus A3 squared. And it's a similar diagram to get you to that point, but it's a lot harder to see 3D on a flat 2D space. So let's talk about an example like from your homework, and it says find the length of a vector. We could pick any of them. So let's let A equal let's let A equal negative 3, 4. Oh, let's do a 3 space. We could do a 2 space. Let's go ahead and do the 2 space. So let's let A equal negative 3, 4. Then we can say that the length of A, or the magnitude of A, is the square root of A1 squared plus A2 squared. So we're going to take negative 3 squared plus 4 squared. So we get the square root of 9 plus 16, which is 25, and that gives us 5. Nice Pythagorean triple there, isn't it? All right, so then let's let A be a 3 space. Let's say 7, negative 1, 4. Then the length of A is equal to the square root of 7 squared plus negative 1 squared plus 4 squared. I'm sorry, I'm not sure why my screen is moving. So the length of A, I moved it that time. So the length of A is 49 plus 1 plus 16. So it's the square root of 66. 50 plus 16 is 66. And that's 6 times 11, which doesn't break down, so it can't be simplified any further. And that's how you find the length of A. So when we talk about adding vectors algebraically, we add them component-wise. That's the way we say it, is component-wise. So look, we have A is A1, A2, and vector B is B1, B2. Notice they're in bold, so they don't need the vector notation. In a textbook, they can use bold, but on paper, we use vector notation. So then A plus B says we take A1 plus B1 for the first one. And for the second one, A2 plus B2. If we were subtracting, we would subtract them component-wise, A1 minus B1, A2 minus B2. If we multiply by a scalar, we do it component-wise, CA1, CA2. And the same rules apply when you look at 3 dimensions. So it's not too bad to work with that algebraically. Let's look at a couple of examples. Let's let A equal, vector A equal the vector of 403, and vector B become the vector negative 215. So let's find, now you could find the length of A and B. We don't need to, we've already talked about that. So number one, let's find vector A plus B. So we're going to add 4 plus negative 2 to be 2, 0 plus 1 is 1, and 3 plus 5 is 8. Number two, let's do vector A minus vector B. So we're going to take 4 minus negative 2 to be 6, 0 minus 1 to be negative 1, and 3 minus 5 to be negative 2. Number three, let's put a 3b, 3 times vector b. So that means we're going to multiply all those by 3, so we get negative 6, positive 3, and 15. And then we can make it fancy and put a scalar with addition or subtraction. So we're going to say 2 times vector A plus 5 times vector B. I find that it's too many numbers in my head to do it all at the same time. So I'm going to multiply by the scalar first and say 2 times A is 806 plus 5 times vector B is negative 10, 5, 25. So now when we add them, 8 minus 10 is negative 2, 0 plus 5 is 5, and 6 plus 25 is 31. There are properties of vectors, and if you look at them, remember that all the pieces in the vectors, all the components of the vectors are real numbers. So when we start with number one, the commutative property holds A plus B equals B plus A. Let's look at that real quick. So if we take vector A plus vector B, we're going to do it in 2 space because it's just less writing. So A1, A2 plus B1, B2. When you do a proof, please keep the end in mind. You generally work on one side and then make it match what you want it to be. So let's add these component-wise, A1 plus B1. Oops, that's not what needs to go there, comma, A2 plus B2. And then since A1 and B1 and A2 and B2 are real numbers, we can use the commutative property inside because these are numbers. So we have B2 plus A2. And then we can separate them back out into B1, comma, B2 plus A1, comma, A2. And this equals vector B plus vector A. So that's not too very difficult. Number 2 says the associative property holds, and it's true. Number 3 says the additive property for the additive identity is true. So A plus the 0 vector. So that would be A1, A2. Let me get a little bit of space here. Plus 0, 0 equals A1 plus 0, A2 plus 0. So this is A1, A2, because when you add 0, you still get 0. So this is vector A. So you can see that the identity property for addition holds. The additive inverse property holds. The distributive property times the scalar holds. The distributive property times a vector holds. The associative property for scalars and 1 times a vector is still a vector. And notice that 1 is a scalar, so it's the multiplicative identity. So each of these is pretty easy to prove if you have to do it. It's not real bad, and they're easy to see and do. You can also look at them, in terms of doing a graph like we did earlier. Let's go back to the top here for a minute and talk about this right here. It says if A, B, and C are vectors, then V sub n and C and D are scalars. I kind of skipped right through that. But when you're working in two space, then we call this V2. So we're vectors in a two-dimensional space. And if um, if you're working in R3, then our vectors are in V3, which is the set of all three-dimensional vectors. So V2 is considered to be the set of all two-dimensional vectors, and V3 is the set of all three-dimensional vectors. Now you could have more than that. It's just we can work with them. V3 is the set of all three-dimensional vectors. It's really hard to work with a 10th dimensional vector and know what's going on. Four-dimensional vectors are used in relativity theory, and the first three components specify position in space, and the fourth component represents time. So it's not something we're going to deal with, but we could work with vectors in 3 space, 4 space, 5 space. So you have more components. It's not a lot harder, but it's harder to think about conceptually. Now, since V3 is the set of all three-dimensional vectors, I don't know why I'm writing it again. Neither do you. It's okay. Since V3 is a set of all three-dimensional vectors, it's something that you need to have heard. So there are three very important vectors. The first one is I. Notice it's a curvy I with a tail, so you can tell it apart, and it is the vector 1, 0, 0. And the second one is vector J. We tend to write it with the cursive J with the vector notation, and it's 0, 1, 0. And the third one is K, and it's the vector 0, 0, 1. Now in two-dimensional space, they don't look like that. That one's in the three-dimensional. We're going to talk about two-dimensional first. So in V2, we would have I equals 1, 0, and J equals 0, 1. So I is 1, 0, so it's right here on the x-axis. This is I, and J is 0, 1. So you can see it there. These are your standard basis vectors. It has a unit of 1. It has a length of 1. Yeah, kind of like the unit circle. So these are important things that are used a lot in our higher mathematics when we're talking about three-dimensional spaces. So here's my V3. So if you look at it, I'm going to go 1. This is I because it has the length of 1 on X. And then J has a length of 1 on Y. And K has a length of 1 on Z. So those are your three-dimensional standard basis vectors. Now, these are something you should make a note of, and they're going to come into play. Let's look at one way in which we use them. So let's think of A in 3 space. We're going to work in 3 space as A1, A2, A3. Now, what we could do is we could write this as, we could split this up into A1, 0, 0, plus let's put a 0 here. I messed that up. 0, A2, 0, plus 0, 0, A3. And then if you think about it this way, this could be A1 times the vector 1, 0, 0, plus A2 times the vector 0, 1, 0, plus A3 times the vector 0, 0, 1. So then this would be A1 times I plus A2 times J plus A3 times K. And why would we bother to do that, you ask? It's because any vector in 2 space or 3 space can be written in terms of the standard basis. So let's say that you're given the vector 1, negative 2, 6. This can be written in that same format. So we'd say 1 vector I minus 2 vector J plus 6 vector K. You could leave the 1 off and just call it I minus 2j. We will because we're higher level math and we don't tend to write the understood one. So you have I minus 2j plus k. It comes in handy to be able to use that notation in cases. So everything we did with vectors before, we can do again and use the ijk notation. So let's say that a equals, let's use the one, let's say vector I plus 2j minus 3k. And let's let vector b, I forgot my vector notation there, and vector b be 4i plus 7k. So now you could add vector a plus b. So you're going to add them component wise again. So you have one vector I plus 4 vector I makes 5 vector I, but we don't say the word vector over and over. And there is no j in the second one, so we just have 2j. And we have minus 3k plus 7k makes plus 4 vector k. So you can see that this works very much like it did before. We could take the time to write out all the steps in between, but we didn't really need to. Number 2, let's say 2 times vector A plus 3 times vector B. Again, I would start with multiplying them, so multiplying the scalars so we don't lose things. So we're going to have 2i plus 4j minus 6k. You don't have to read the word vector every time as long as you remember to write it. And then when we multiply 3, we have 12i plus 3 times 7 is 21k. So when we combine these vectors, we end up component-wise, we end up with 14 vector I plus 4 vector j, and then plus 15 vector k. So again, we're not changing what we did before. We're just we're going to have two notations. We have a notation component-wise. We have a notation using the standard basis vectors, and we can do things graphically. So let's look at the next formula, the next concept. The next concept is the unit vector. Now, a unit vector is just like it. A unit vector is just like it sounds like. It has a unit of 1. A unit circle is a circle with a radius of 1. So a unit vector is a vector whose length is 1. So if we were to go back to the other one, I, j, and k are all unit vectors because they have a length of 1. If you find the length of I, you find 1 squared plus 0 squared plus 0 squared to be square root of 1, which is 1. And that's true for all of them. So they are all unit vectors, unit vector of length of 1. So for any vector, this is what's important here. When you have a unit vector, the unit vector, we're going to call it u, vector, obviously. 1 over the length of vector A times vector A. So it really is vector A over the length of A, vector A. So if you think about what that means is if you take each component and divide it by the length, then it will end up with a unit vector of 1. Let's look at an example. We need to make a note here. Note, A cannot be the 0 vector. Why is that? Because you can't divide by 0. So we have that note, and let's boil it down into vector A over the length of vector A. So let's do one of these. Let's say that we're given vector A to be 2i minus j minus 2k. So if we want to find the unit vector for this, the first thing we have to do is find the length of A. So let's erase our unit vector here, and let's come back to it in a minute. But let's find the length of vector A. So component-wise, we're going to take 2 squared to be 4. And then negative 1 squared is 1, plus 2 squared is 4. So this is the square root of 9, which is 3. So then for our unit vector, we're going to put 1 over the length of A times vector A. We tend to write it out front as a fraction. 1 over 3. The length of vector A is 3. Now, we're in IJK format, so we tend to stay in IJK format. We tend to not bounce back and forth. So we're going to say 2I minus j minus 2k. So we could leave it like that because it works, but our unit vector then is 2/3 I minus 1/3 j plus 2/3 k. Now you could verify that that has a length of 1. Let's just throw it over here on the side. It's not important. We don't really need it. So the length of u would be the square root of 2/3 squared is 4 over 9 plus 1 over 9 plus 4 over 9, which is the square root of 9 over 9, which is 1. So this is the unit vector for A. What that means by it being the unit vector for A means that it is the length, it is the vector in the same direction, but it only has a length of 1. So let's talk about what that means in the graph. Oops, there we go. Let's talk about what that means in the graph. So let's graph our original vector. So we have 2, and then we have back 1. So that gives us this piece of this box. And then we're going to go down 2. So that means that our vector, it sits right here. It doesn't sit on the x-axis, it just looks like it. And then if you were to take and do the other one, it's shorter. It has a length of 1 total. So it would come up 2/3, back 1, and down 2/3. So it sits on the red. It just is not as long. It has a length of 1 total. So this is our unit vector here for the given A. Before we get into applications, there's, I think, one in your homework that we need to talk about, so it kind of makes sense. It says, what is the angle between the given vector and the positive direction of the x-axis? So the angle between the given vector is 24i plus 9j. Now, since we only have two vectors, since we only have two components to the vector and they're I and j, that does not mean that the k is 0. It means we're in 2 space. So we're going to look at this in V2. If it was not, I and k, then we'd be in V3. So let's look at xy axis. We have 24i, so we're going to come over about 24 and go up 9. So I would say it's in here. This is 24i plus 9j. All right, so you're looking for the angle between this and the positive x-axis. I didn't finish writing the problem out. And the positive x-axis. So you can see that we're looking for the theta here. And we're going to work in degrees, not in radians. Now we know that this length right here is 24. And we know that this length here is 9. So that means that we can do tangent of theta equals 9 over 24. So theta equals, and you need to pull your calculator and do it for me. I got 20.55 degrees. Now, generally, the rule of thumb for a lot of people is we were given whole numbers. So we're going to go to tenths. I just like a standard 2 decimal places. WebAssign is going to say round to the nearest degree, which is 21 degrees. So that's not too bad, but I think it's helpful to see it. And then there's one more. A pilot is steering a plane in the direction of north 45 west at an airspeed of 180 miles per hour. So here's my plane. North is up, north, east, which we don't need, south, which we don't need, and west. Now, north 45 west means that we're coming from the north 45 degrees towards the west. So we're going to draw this triangle to go here because that's where we're traveling is north to west. That's where that angle is. So this is our x value, and this is our y. Now, we also have a speed of 180 miles per hour. So the vector of the plane is found using these values. Let's start with cosine. Cosine of 45 equals, cosine is y over 180. So I don't know why I started with cosine, but I did. So y equals 180 miles per hour times cosine of 45. We're going to leave it in that format. And then sine of 45 equals x over 180. So x equals 180 times sine of 45. Now, the problem is we are working, this x is technically negative because of where it sits. So we need a negative on the x value here. So we have a negative on the x, and we're going to keep it with the 180 and move it over there. Does that make sense? Take a minute and process that. So then the vector of the plane is going to be, we can write it one of two ways, negative 180 sine of 45, comma 180 cosine of 45. Or we could write it as negative 180 sine of 45 I, vector I, plus 180 sine of 45 vector J. Either way, whichever works. I like vector notation. It's easier than writing the vectors of I and J. Now, in the second one, it says the wind is blowing in the direction of south. So here's our south and headed towards east. So that means it's going to come here with the 30 degrees in between. And let's draw our triangle over. This is our x and this is our y. And it's at a speed of 35 miles per hour. So that means that, let's start with sine. Sine of 30 degrees equals x, which opposite over hypotenuse, x over 35. So x equals 35 sine of 30. And the x is positive. In this case, the y is negative. So keep that in mind. We have cosine of 30 equals negative y over 35. So put the negative on there and say y equals negative 35 cosine of 30. All right, so now let's talk about the vector of the wind. The vector of the wind is equal to negative 35, positive 35 sine of 30. The y value here is negative 35 cosine 30. So now we're supposed to be looking for the true course and the ground speed of the plane. So let's talk about in order to find them, we need to find the vector of the combined values of the plane and the wind. Notation, notation, notation. Let me run back. Okay, so this could be very hard, but go ahead and use your calculator. Pause it, make sure you're in degrees, run those numbers on your calculator, and then come back. All right, go for it. So I got negative 109.779, and the y value is 96.968. So when we're looking for the ground speed of the plane, if you go back up here, the speed, if we look up here, the speed was the length of the vector. So if I find the length of this combined vector, that's going to give me the speed of the plane. So we're going to take negative 109.779 quantity squared plus 96.968 quantity squared under the square root. Now remember, if you don't round off those values and use the whole value on your calculator, then you'll have a better answer, but you should be able to do it either way in WebAssign, unless it says do not round anywhere in the middle. You know how to handle that, so I'm going to let you do it. So when you take the square, you're going to do the squares and the addition of it, and then take the square root of it, all that stuff, and we get 146.473. And that's in miles per hour. This is the ground speed of the plane. 146.473. Now we're going to look at this graph and look at this on the graph. We're looking for the true course. So that means we need the angle. So we're going to draw this on a graph, our X and our Y graph. It's a crooked line, but we're going to run with it. And it's negative 109 and positive 96. So negative 109, come over about here, positive 96, maybe a little higher. It doesn't matter, it's a sketch. So we have a vector here, and the length of that vector is 146.473. We could write that on 146.473 because it's the length of the vector and it's the speed, it's miles per hour. So we're going to put our theta in this triangle as it was before. So here we have north and west because that's the main vector. The wind is not as fast as the plane, but it takes us back to this vector and what we have here. So if we think about this triangle and what we have, the x is negative 109.779. And we don't really need the negative because it's an acute triangle, so we want a number less than 90. And then the height here is 96.968. So if we say tangent of theta equals opposite over hypotenuse, we have 109.779 over 96.968. So theta equals inverse tangent of that fraction. If you plug that into your calculator, you get 48.5 degrees. So theta is 48.5 degrees. So the true course is north, 48.5 degrees west. So that's our true course, and this is the ground speed of the plane. So there you have everything about vectors for this section, including an application that hopefully you enjoyed. And I hope you have a great day.